In this video, we're going to do example 2.4.1, which is part of the unit on section 2.4, shortest distances and closest points. In this example, we're going to implement the procedures that we talked about in the last video, in particular how to find the distance and the closest point from a point A to a line L. So we're given point A, which is the point 211, and the line L, which is x is minus 1 plus t, y is 8 plus 2t, and z is 8 plus t. And we're asked, first of all, to show that, in fact, A is not on L. So this is something that we've done before when talking about lines. So let's remember that to do so, we are going to plug in the x, y, z as the coordinates of A. So 2 is minus 1 plus t. 1 is 8 plus 2t, and 1 is 8 plus t. And for A to be on L, it has to be a single value of t that works in each of those. So let's solve the first. We're going to get t is equal to 3. If we solve the second, we're going to get t is minus 7 over 2. That's obviously a different value. And so that means our little system is inconsistent. And if the system is inconsistent, then we can say that A is not on L. So let's look at part B. And part B is asking us to find the point Q on the line that is closest to A. So let's give ourselves a little diagram here. Always, always, always a sketch to orient yourself, but also to orient the person or people reading what you're doing. So we have a point A which is not on our line L, and we're looking to find the point Q on L, which is the closest. And if it's the closest, then the dotted line that I've drawn there is a perpendicular distance. So we can see a couple things about L. We can see a point P on L, which we can read from the parametric equations as the point minus 1, 8, and 8. A was the point 2, 1, 1. And we can also see the direction vector being used for L, which is the coefficients of t, so 1, 2, 1. And we are going to create the vector PA from P to A. So PA, I'm going to subtract the components. So components of A minus components of P. So 2 minus minus 1. 1 minus 8, and 1 minus 8. So there is our vector PA. Now, vector PQ here, vector PQ, which I'm going to use to get from P to Q, is the projection vector. So PQ is the projection of PA onto D. And if we remember our projection formulas, that was PA dotted with D over the magnitude of D squared, all of that times vector D. So PA dotted with D, that means we're taking PA here, we're going to dot with D there, and so doing the dot product, we get 3 times 1 is 3, minus 14 and minus 7. Divided by the magnitude of D squared, so that's 1 squared plus 2 squared plus 1 squared. And that is going to be then times vector D, 1, 2, 1, which gives us, so 3 minus 14 is minus 11 minus 18 divided by 6 times 1, 2, 1, that's very nice, that gives us minus 3, so our projection vector is minus 3, minus 6, minus 3, and now we're going to use that to find point Q, so the position vector of Q is OP plus PQ. Well, we now have both of those. OP is minus 1, 8, 8 plus PQ, that's the projection vector we just calculated. Add those together, minus 1 plus minus 3, so minus 4, 8 minus 6, 8 minus 3. That's the position vector of Q. Therefore, point Q has coordinates that match, so minus 4, 2, 5 is the point Q on L that is closest to A. Point C, or part C, has us calculate the distance from A to L in two ways. First, by using the norm of the vector QA, and second, by using the distance formula. So let's start with the norm of vector QA. That is the vector here from Q to A. So vector QA will calculate by subtracting the components of A minus the coordinates, the coordinates of A minus the coordinates of Q. And so I'm going to get 2 minus minus 4 is 6, and 1 minus 2 is minus 1, 1 minus 5 is minus 4. So this is the distance that we're looking for. So the distance from A to L is the magnitude of that vector, 6 minus 1 minus 4, which is the square root of 6 squared plus minus 1 squared plus minus 4 squared, which is going to give me 36 plus 1 is 37, plus 16 is 43, 53, the root of 53 units. Now we're going to do the distance formula, and we should get the same answer because we're calculating the same distance, obviously. So let's remind ourselves what the distance formula was that we saw in the last video. So the distance from A to L can also be calculated as the norm of PA cross D divided by the magnitude of D. So we have to calculate the cross product. So we need PA crossed with D. PA is the vector that's sitting up there above. So 3 minus 7 minus 7 crossed with vector D, and vector D was 1, 2, 1. So crossed with 1, 2, 1. Let's calculate that. So 3 minus 7 minus 7, 3 minus 7, 1, 2, 1, 1, 2. So what do we have here? We have minus 7 minus minus, so plus 14, which is going to give me positive 7. We have minus 7 minus 3, which is going to give me minus 10. And 6 minus minus, so 6 plus 7 is 13. And that lets us calculate here the norm of that cross product is the square root of 7 squared is 49, plus 10 minus 10 squared is 100, plus 13 squared is 169, and divided by the norm of vector D, so 1 squared plus 2 squared plus 1 squared. Now if we do a little simplification, we can bring this fraction under the root. 49, so 100, 169, 269, plus 49, we get 318 divided by 6. And if you check, 318 divided by 6 is indeed 53, so the root of 53 units, whether you use the distance formula or you use the norm of vector AQ. Incidentally, vector AQ is the orthogonal component.